welcome to the Dynamics tutorials. So with this problem, we're going to use the radial and transverse coordinate system to solve a problem where we're going to calculate the velocity and acceleration of a particle that's constrained to move along this curve where we have r as a function of theta. So r is equal to 300 millimeters times cosine of theta. We're looking at the velocity and acceleration exactly at this point when theta is equal to 20 degrees, and we have this information that theta dot is 2.5 radians per second, and theta double dot is 0.3 radians per second squared. So here's our curve that's generated by r is equal to 300 cosine of theta. Here's our particle. Here's our angle of 20 degrees. And then our radial direction is going to go in the direction of increasing r out here. And our theta, or transverse direction, is going to go perpendicular to the r in the direction of increasing theta. So really, when we're working through one of these problems, they look complicated, but we really just need to always set up our table. Our table is going to have our theta dot, and our theta double dot, in this case just from the problem statement. And then we'll need to do also our r dot, and r double dot. So in this case, our r, we can take our expression here and just plug in theta is equal to 20 degrees and get our r. For r dot, we'll need to take a derivative of this with respect to time. So derivative of the cosine of theta is going to give us the negative sine of theta, but since it's a derivative with respect to time instead of theta, we'll need the derivative of the argument here. So we'll need a d theta dt, which is our theta dot. Plugging in our theta and our theta dot here gives us negative 257 millimeters per second. And then for our double dot, we'll take another time derivative of this. This is now two products. So we've got, one product of two things multiplied together. So we have sine of theta times theta dot. So we need to take a derivative of the sine of theta and get a cosine of theta, which gives us another theta dot since we're taking the derivative with respect to time. And then over here, we'll take the derivative of the theta dot portion and get theta double dot. Again, we'll just plug in our values from up here, and we'll get negative 1793 millimeters per second squared. From here, it's just a plug and chug into the formulas for the radial and theta components of the velocity and the acceleration. So velocity in the r direction is just r dot. We've already calculated that, so we plug that in here. Velocity in the theta direction is r times theta dot. So we plug in our r, plug in our theta dot, and get 705 millimeters per second. And then our acceleration in the radial direction, the formula is r double dot minus r times theta dot squared. Plug it all in, get 3.56 meters per second. And then for a theta, we have r times theta double dot plus 2r dot theta dot. Plug it all in, and we get the negative 1.2 meters per second squared. So we've got the velocities here, and we've got the accelerations here. If the problem had asked us for a magnitude of the velocity or a magnitude of the acceleration, you just need to take each component, square them, add them together, take a square root. Thanks for watching.